Thanks, and thank you very much for putting together such a nice program. It's always nice to bring together different physicists and mathematician audiences. And yeah, thanks for making it work under these extremely hard circumstances. I joined Slack, so people should feel free to ask questions there, even after the lectures or after the watch parties and so on. So, and I'll also upload the result of the lecture there. So maybe let me start with a disclaimer. I'm a physicist, so I will try to explain things in a language I think is okay for mathematicians, but if it's not, just stop me and I'll do my best to try to translate to the best that I can. So these lectures will be on obtaining a vertex operator algebra inside any four-dimensional superconformal field theory with n equals 2 supersymmetry or higher. So I'll focus mostly on n equals 2, but you can keep in mind that if you have more supersymmetry, just come along for the ride. And the way I structure these lectures is that in the first lecture, I will basically introduce what are these things. So what are four-dimensional superconformal field theories and why do I care with all of this? And also how do vertex operator algebras help? So this is a little bit the plan. The first lecture is introducing the players. And then in the second lecture, I will construct a map between four-dimensional n equals 2 STFTs and vertex operator algebras. And then we'll go on in the third lecture to study the properties of this map and the consequences for four-dimensional physics. Okay, so let me start with introducing n equals 2 STFTs. So I'm telling you I'm finding a map between some theories in 4 dimensions. So how would you specify a theory? What is a theory? If you're a physicist, typically you start by giving some sort of microscopic description in terms of fundamental degrees of freedom. So most commonly, you would give a Lagrangian description in terms of a gauge theory. So I would say I have some gauge group that can even be some product. And now I have gauge fields. And so I will write the field strengths that transforms in the adjoint of the gauge group. But we have supersymmetry, so I'm interested in theories with n equals 2 supersymmetry. So each field comes accompanied by superpartners. I have n equals to Susie, means I have supercharges. And I'll call them Qi, and n equals 2 means that I have 2 of them, and they transform as spinors. So this alpha is a spinor index that can be plus or minus. And I also have a Q tilde alpha dot, which is a conjugate spinor. That's, let me call them plus dot and minus dot. And again, I, which is 1 or 2. And these supercharges, if you're familiar with supersymmetry, know they take you from bosons to fermions and vice versa. So the fact that I'm demanding I have a gauge field, which means I have a field strength that's a boson, it means they will come, these field strengths will come accompanied by other fields, and some will be fermionic. So what I have is the field strengths, but then I also have to have two wild fermions. So let me call them lambda I. And they are fermions, so they carry a spinor index. And it turns out I also have to have a complex scalar. So altogether, this guy is what is called the vector multiplet. And it must be in the adjoint of the gauge algebra. So this is the field strength is a dimension 2 operator. These guys have dimension 3/2, and free scalar has dimension 1. So these are all free fields, as you would normally do to write down a Lagrangian. So this means that they all satisfy the corresponding equations of motion. And I've grouped them together in what is a representation of the conformal algebra, and we'll get more into this in a minute. So n equals to Susie requires they come as this package. This is a representation more soon. So if you want to write a gauge theory, then you start by adding vector multiplets. And now you want to add matter to this. So then for the Lagrangian, you want to add matter in some representation of G. And again, the matter I want to add should be consistent with n equals to supersymmetry. And so it turns out there's only one type of matter I can add. That is hypermultiplets. So these are, again, they form, it's always the same spirit. Supersymmetry relates different operators, bosons and fermions. So I start with a scalar, actually a doublet of scalars. These are scalar. And again, they're free operators. They have dimension 1. And then supersymmetry requires that I also have two fermions like that, again, of dimension 3/2. So this is actually a half hypermultiplet. I will demand that it transforms in some representation R of G. And to have the complete thing, I need to add the CPT conjugate in the representation R bar of G. So in the conjugate representation, so I doubled this. And note, and we will go a little bit more into this, how short this representation is. So I'm telling you that if I'm searching for representations of the conformal algebra or the superconformal algebra that contain free fields that I can write in my Lagrangian, I find the vector multiplet that has dimension 1, 3/2, and 2 operators, and then I have hypermultiplets that are extremely short. It's an ultra short multiplet. And this is related to the fact that all of these operators are conserved. So again, these scalars are conserved, and they even obey other shortening conditions. For example, that the supercharges kill this guy here. So these are examples, and we will systematically study what is the representation theory of the n equals to conformal algebra. But here we're finding in examples, when we start writing down free fields, already examples of particularly short multiplets. So now to write a Lagrangian, you just take these two guys together. You add vectors in a joint of G, and then hypermultiplets in representations of G. And you want to, I'm interested in not only supersymmetric series, but also conformal series. So I need to impose conformal invariant. So I should impose that the beta function vanishes, so that I have, so this constraint the type of method I can add in my Lagrangian. And then it's an exercise in constructing these Lagrangians. The classification has been done. So this fixes what method you can have. You can classify Lagrangians reserving both SUSY plus conformal plus done by these authors in 2013. And the Lagrangian is completely fixed by symmetry up to the gauge couplings. And these are the things that parameterize the conformal manifold. So they are exactly marginal deformations, and you can tune them as you move in the conformal manifold. So this would be the typical Lagrangian theory. You write down your Lagrangian, you impose that it obeys everything you want it to obey. Then you have some parameters which parameterize the conformal manifold. It tells how strongly coupled the theory is. You start from a weakly coupled point, and then you can crank up the coupling. And you can start writing operators in this theory. And operators, as you well know, should be gauge invariant. And they are gauge invariant combinations of the free fields I put in. For example, I can write this guy. Remember, this was the scalar in the hypermultiplet. I told you it should transform in some adjoint, in some representation of the gauge algebra. And then I need the conjugate, another hyper in the conjugate representation. And I contract the indices to make it gauge invariant, and this would be an example of an operator in my theory. And I could try to use Lagrangian to compute correlation functions, which are the observables in my theory. And now however, if you start playing with these series, you soon realize that the landscape of n equals to superconformal field series is much more diverse than this. And there exists isolated superconformal field series that don't have a conventional Lagrangian description in this sense. And you can land onto them just by start by playing this game. So let's say I wrote a Lagrangian in some weakly coupled limit, and now I start computing stuff, and I want to increase the coupling. I increase from 0 coupling up to some strong coupling value, and then I might find that as I crank up the coupling, I end up in some corner where I have another description, a dual description, in terms of another weakly coupled theory. But now the building blocks are no longer these two basic guys I introduced, the free vectors and free hypers, but they are now strongly coupled building blocks that are isolated theories, and that you need to construct the description of the series you started with. You need to take these isolated, strongly coupled building blocks and gauge them to other building blocks or to free hypers and vectors. So then you realize that the landscape is much more rich and diverse. And we need to find, well, it's useful to think about this without having to refer to free fields. Okay, so if there are any questions, this is the motivation of why we're going to go the way we are. But if there are any questions, please feel free to ask.
I don't see any in the chat box yet, but does anyone have a question? You can raise your hand also. I had a quick question. So you mentioned, you're building your theories starting from a Lagrangian.
Yes.
And you had this classification of the Lagrangians. There are theories that don't necessarily come from a Lagrangian, right?
Exactly. So this is where I wanted to go exactly now.
Great.
So what I told you is how you'd go about constructing Lagrangian series, and you might think this is enough. But even if you just start from this Lagrangian series, let's say start from one of these. And now increase the coupling. And you will find that in what looks like a strong coupling point from the original description, you can actually describe it as, you can find a dual description for it in terms of another weakly coupled theory, but now the building blocks are not just free hypers and vectors. So you can find so now you find new non-Lagrangian, or let me write just new building blocks that do not admit a conventional Lagrangian description. So it could be that I started from free vectors plus hypers, and this is a good description of the theory in some region at weak coupling. And now as I increase the coupling, I find a different region that has a dual description. Again, in terms of something that is weakly gauging something, but now what I'm weakly gauging are not free factors and hypers. So now here I would find, for example, some isolated, strongly coupled, or isolated is enough. It's a series that has no exactly marginal deformations. For example, Gayoto's TN series. That has flavor symmetry. So now you can have various of these isolated building blocks, and now you gauge. So the dual description is that you gauge weakly this flavor symmetry. So even if you start just from Lagrangians, there's no way around the need for series that don't have a conventional Lagrangian description in the sense I described. And so then instead of trying to write things in terms of the fundamental fields of the free hypers and vectors and then building everything out of those, I want to avoid having to describe a Lagrangian altogether and just start by telling you the observables. And in the end, my observables, if we go back here, are operators like this. They're gauging variant. And I don't care about how they were made up. I just care that this guy exists. So then I just describe the theory instead of giving the free fields and then making composites out of them. I just describe the final products. I just describe all operators I can have in my theory and all their correlation functions, which are the observables. So this motivation was to justify why. So this motivates us to take an abstract approach. And we describe a theory by giving a list of operators and all their correlation functions. And these are my observables. This is what I can in the end. So I don't need to know how you got this theory. It can be a Lagrangian or it can be one of these new isolated theories. In the end, all I need to know is this. So then you give me the list. For example, you tell me that this operator is there in the theory. Okay, so this means I now must take very seriously my symmetry algebra, and I need to figure out, instead of starting from fundamental building blocks and just building out of there, I just need to take an abstract point of view and list all possible representations of my symmetry algebra. So as Aswin was saying in his introduction, representation theory plays a very important role here in physics, because to take symmetry seriously, I need to know operators must be organized. So they must lie in representations of my symmetry algebra. That's what it means to have the symmetry. So now I need to work out representations. I need to work out the representation theory of the n equals to superconformal algebra. So this might sound like a technical thing that would best be avoided, but it really becomes necessary if you can no longer rely on just building your operators out of 3 fundamental fields. So I will start by quickly reviewing representation theory of just the conformal algebra, and then I will see how supersymmetry organizes this on top. So I will start with a quick summary of conformal algebra and its representations. Okay, so if I'm in Lorentzian signature, the conformal algebra is SO 4,2, and it would have been SO 5,1 if I were in Euclidean, and the generators are mu. So the Lorentz algebra dilatations, translations, and special conformal transformations. And I copied them down here. So the particular details of the expressions are not very relevant, but just the thing that comes out of it is. So these guys, they generate the Lorentz algebra. So this is SO p minus 1,1 in Lorentzian signature, and here these etas are the metric on R3,1 if I'm in Lorentzian, or if you want to rotate, they would be on R4. And then we see here that P mu and K mu are Lorentz vectors. All commutators I have not listed vanish. And then we see that P mu and K mu act as lowering and raising operators. For D. So the increase, this is called the dilatation operator. And P and K increase and decrease the value of D. So now we can build representations just like we would build representations for SU2, for example. So we start by diagonalizing the action of the dilatation operator. So we say that we have an operator that obeys. We diagonalize the action, and operators have some scaling dimension. So this is what I will call the scaling dimension. And then dimension must be bound from below. So if K reduces the scaling dimension, at some point it must kill the operator, otherwise I would have unbounded dimensions. So at some point K mu must kill, and this is what this guy becomes called a conformal primary. And I build my whole representation by acting with momenta, by acting with the translations P mu. So this becomes del mu O, and so on. And this increases the dimension. So this guy has dimension delta plus 1, and so on. So this is what is called, that is what I would, as a physicist, call a lowest weight state. So I have a lowest weight state of my conformal algebra, and then I build the whole representation by acting with momenta. And now I forgot about the Lorentz generators. They commute with the D's, so they don't change the dimension of the operator, which means that I can just organize this operator in representations of Lorentz. So this guy now is in some representation of Lorentz. And this whole thing together is what is called the conformal multiplet. So it's a conformal primary that is killed by the special conformal transformations. And it has some definite weight and it transforms in some representation of the Lorentz algebra. And then I build the whole module by acting with p mu's, with momenta. And acting with momenta is just acting with derivatives. So I just get the whole conformal multiplet. Now we want to build superconformal ones. So now to add supersymmetry, I need to consider the n equals 2 superconformal algebra. So let me write down the algebra. This is U2, 2/2. So this is a Lie superalgebra. And for the more mathematical oriented, this is just a Z2 graded algebra. So something like this, where for physicists, these are the bosonic generators. This is the bosonic part, bosonic algebra, that is also called even in the math literature. And this is the fermionic or odd. And this algebra comes equipped with a bilinear product. So for physicists, these are commutators and anti-commutators that has the property, the symmetry, it's either symmetric or anti-symmetric under the exchange of the two things following this. Where I am using the I to say that AI is in GI and BJ is in GJ. And then here, there's this sign that depends on whether it is. So again, for physicists, this is just saying that if they're both fermionic operators, you have the anti-commutator. And if one of them is bosonic, then you use commutators. So this is just saying. Okay, and this product is consistent with grading. This is in GI plus J mod 2. So basically it's G0 if I equals J and G1 if I is different from J. And it obeys graded Jacobi identities. So for mathematicians, this is the formal definition of super Lie algebra. For physicists, we have fermionic and bosonic generators. And now we have commutators or anti-commutators depending on the type of things you're commuting. So here G0 is a Lie algebra. And having in mind the particular superalgebra I want, so n equals 2 superconformal symmetry in 4 dimensions, G0 is the maximal bosonic subalgebra, which is the conformal algebra in 4D. And then there's an R symmetry. So this here is called an R symmetry. So it commutes with the conformal algebra. We will see how it acts on the fermionic generators. And so it's generated by an R plus, an R minus, and an R. So these are SU2R that I'm writing in a tiny R for the U1. And the conformal algebra is the one we just had above, so it's generated by P mu, K mu, M mu, and D. And then we have that U1 is a G0 representation. So these are my fermionic generators, and I'm just saying that they transform in some representation of the bosonic algebra. And so these are my supercharges. And they are fermionic, which means they are also nilpotent. So I already had written before, but let me write it now in complete detail. These are my supercharges where I equals 1 or 2. So this is because n equals 2. And then I have another. So these are spinors of Lorentz. So you see they transform in some representation of my bosonic subalgebra. They are spinors of Lorentz. They have weight a half, and they transform in some representation of SU2R. So SU2R rotates them, and they are charged under U1R. So I wrote here half of the supercharges so far. I need to write 2 more. These are the ones called Poincaré supercharges, and then I have 2 more, which are the conformal supercharges. Okay, maybe I see that there are questions. Maybe I should pause here and answer them before moving on.
Sure, yeah. Would you like me to read them out? Or?
So there's a question on the importance of the square bracket and curly bracket. Okay, so this was just kind of a notation to say that I will be using 2 different. So let me write this out, and this fits nicely with what was going to come. So what this means is that I have this product that depends on its properties. It's either symmetric or antisymmetric under the exchange of the 2 things. And it depends on the type of, having bosonic or fermionic operators there. So what I will use is basically that it will be a commutator like this. If A or B is in G0, so it's bosonic, and it's the anti-commutator if A and B are in G1, so they're fermionic. So when I'm agnostic, when I don't know what these guys are, I put the square bracket on one side and the curly bracket on the other. just to remind you that you should use one or the other depending on both what type of operators you're commuting or anti-commuting. And so then the superalgebra that I want to study is this one. This is the one for four-dimensional n equals to superconformal field series. And the bosonic piece is just the conformal algebra. And then there's something else that is called an R symmetry. That was a question about. So the R symmetry it's a bosonic symmetry. It's just an SU2R and a U1R. And its significance comes from the fact that the supercharges are charged under it. So they are doublets of SU2R. And they are charged under the U1R. So now my whole so n equals to superconformal algebra is generated by the set of fermionic generators I just wrote, and let me omit the indices, Q, Q tilde, S, and S tilde, but also the SU2R, so R plus and R minus, a U1R, and then the conformal algebra that I had written previously. And yes, as Aswin pointed out, it's important that this SU2R acts trivially, so it commutes the generators in SU2R commute with these ones, and they also commute with ones in U1R, but they act non-trivially on the supercharges because the odd piece, the fermionic piece, transforms as some representation of the bosonic algebra. Okay, so now I've listed what the algebra is, and I haven't written all the commutation relations. I won't write them all out because I think it's not particularly illuminating, but I can give a reference to where they're all written down in all detail. So what I want to do now is that I have the algebra and I want to see how operators are organized. And I want to do similarly to what we were doing before. I want to find highest weight states and build whole modules out of it. And since the conformal algebra is a subalgebra here, I want to see how the conformal multiplets we built are now organized, fit together in a bigger multiplet that is a representation of the n equals to superconformal algebra. So now I want to construct representations of the n equals to superconformal algebra. And if you write down all the commutation relations, you will see that S and S tilde lower the dimension by a half, and Q and Q tilde raise. So again, I will see this as lowering and raising operators when constructing my module, and in particular because Q and the S and S tilde lower the dimension, and I want my dimensions to be bounded from below. At some point, once again, S must kill my state. So I'm always using interchangeably a state and operator, and then in a CFT you have the state operator map. So I jump in between talking about local operators and states. And this is just a consequence of the state operator correspondence in CFTs. So that's why I keep changing my words and either talk about local operators or states. So in spirit, I can now say I have a highest weight state or a lowest weight state, depending on your taste. I like to call them lowest weight state. That is killed by the conformal supercharges, by the S's, the ones that lower the dimension. And because K is proportional, so K, let me even write it all out. So the anticommutator of two conformal supercharges is the special conformal transformation, the case. So because if S and S tilde both kill the lowest weight state, then so will K. So this guy that I want to call a superconformal primary is in particular also a conformal primary. And now I want to act with the Q's to build my whole multiplet. So I act with Q and Q tilde. And I get a new state that now has dimension plus a half. So if this guy had dimension delta, this one has dimension delta plus a half, and I can keep going. Because also the commutator of two Q's, so let me write it down. And here I'm swapping between vector indices and dotted indices, and you can do that using the sigma matrices. So the commutator of two Poincaré supercharges is translation, is P mu. So acting with all Q's, I generate also conformal descendants, but some of these operators will also be conformal primaries. So some combinations in this dot 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 here, some are conformal primaries and some are descendants. So you can now organize this whole thing. It will form now a super conformal multiplet instead of just a conformal one. Didn't work because I didn't close. And it is a sum that is finite of conformal multiplets. So you can think that if you have a conformal multiplet, that starts with some O, W, O, etc., then you can act with the supercharges to make to obtain other conformal multiplets. And you have this finite regrouping, and finite because the supercharges are nilpotent, so I don't get to act twice with the same supercharge. So you have a finite regrouping of conformal multiplets in big superconformal multiplets that are my representations. So I'm saying they're my representations, so I need to tell you what labels I should use. So let's look again at what generators we had. I was starting with the superconformal primary. Just like before, I would like it to have a definite dimension that be an eigenstate of the dilatation operator. It has a definite dimension delta. Can highlight it maybe. And then the dilatation operator commuted with Lorentz. So I had said that this guy should also be in some Lorentz representation. But the dilatation operator also commutes with the R symmetries. So they should also be in some representations of the SU2R. And once you know this, once you know the quantum numbers of the superconformal primary, you act with the supercharges and you know the commutation relations of the supercharges and the various generators. So you can work out what representations all of these operators transform in. So the labels now, so a superconformal multiplet is labeled by the quantum numbers of the superconformal primary. This is the guy killed by S and S tilde. And these are the scaling weight, the dimension, the Lorentz representation that I will use, that will specify as to Lorentz spins. The SU2R representation that I will call R, and U1R charge. And from here, you build the whole multiplet by acting with the supercharges. But now not any representation is something I'm interested in for physical reasons. I'm interested in unitary representations. So I'm studying unitary series. In Lagrangian signature. And this requires that all operators have positive norm. So when I'm building this multiplet and I'm starting from some lowest or highest weight state, depending on what you want to call it, that is the superconformal primary. And now I'm building the multiplet by acting with Q and Q tilde. I need to make sure that all of these guys, all of the superconformal descendants, they must have positive norm. So now I'm talking about the norm. So I need to tell you what is the inner product. I need to recall what is the inner product. So I need to give you what is the emission conjugation operation. And in a CFT, we work in radial quantization. So we quantize our theory in spheres. And the emission operation is, let me call it dagger in radial quantization, is such that the conjugate of a Poincare supercharge is a conformal supercharge, like this. And the conjugate of P is K. And so now what I need to work out is that all norms are positive. So if I have some state that I created like this, now I want to compute its inner product with a different state where I use dagger. And this has to give me a positive semi-definite matrix of inner products. So what this results in is what are called unitarity bounds. That tell you typically that the scaling dimension is above some value, let me call it delta B, that is a function of all the other quantum numbers of the primary. So you get inequalities like this that tell you that the scaling dimension of superprimary is bounded by some function of all the other quantum numbers. And if the inequality is not saturated, you have what is called a long multiplet. This is a generic multiplet. You just act with the Q's and you never encounter any zero or negative norms. You just act as much as you want and you get the whole big multiplet. When the equality is saturated, this is when you get a short multiplet. So the inequality being saturated means at some point in your multiplet, you encounter the null state. So something had zero norm. Below this, you'd get negative norm. At the threshold, you get zero norm. And this means that there's a submodule here. So the representation is reducible. And we want a reducible representation. So we're going to throw away the null states. And in the very beginning, we started exactly with an example of this. So when I was writing, for example, the hypermultiplet, and I had something like this, this multiplet was very short. It was very short precisely because if you acted with the supercharges, you'd get null state, you'd get zeros. And one such null state is the equation of motion. So these things are related. And these multiplets are called short precisely because they are shorter. They have less states than a normal multiplet because you cannot act as much as you want. This means that if you act twice with p mu, you get zero. Sorry. Oh. And then finally, something that can happen is, so let me try to draw here a visual picture of this. So we have the dimension of the superprimary, and this is enough to label the whole multiplet. And we're finding that there's some bound, and all operators must be above here. So this is where our long operators are. If you're exactly at the bound, you have what is sometimes, it's a short multiplet, sometimes these are called semi-short, for a reason that will become clear in a second. And then if you're below, these are non-unitary representations. There are negative norm states. But in supersymmetry, there's an interesting phenomena that there are also representations below at isolated dimensions that are allowed. And these are short or ultra short representations that are, the quantum numbers become much more fixed because you really need to fine tune everything, such that there are no negative norm states, and they're very short because you have many nulls. So the vector and hypermultiplet were actually examples of something like this. So this is a classification game that you can do. You can now act with the supercharges, you know, the commutation relation. I've told you what's the emission conjugation, so you know what's the inner product on this state. So you can just compute norms or level by level and figure out what are the conditions on the quantum numbers such that the norms are all positive. This is an exercise one can do. I won't do it in detail. It was for the n equals 2 superformal algebra. It was done long ago by Dolan and Osborne. Back in 2002. More recently, it was done again in these and other algebras by Cordova, Dimitrievich, and interrogator. And one of the references I gave, which were lecture notes by Eberhard, reviews this. So this means that then all unitary representations have been classified, and they are typically labeled by, they're given a name, but it's not particularly illuminated to just give a list of names, but the names typically encode the type of shortening condition. So they tell you what is the null state. So now closing the loop and going back to how I started. Now, what is a theory? Then if I want you to tell me what is a theory, I would like you to tell me what is the list of all the operators the theory has, but this list organized into superconformal multiplets. So for example, the guy I wrote earlier, and now I don't care how this guy was obtained. I don't need to remember how it was. I don't even need to have free fields to have this operator. I would just say that my theory has this operator. It actually sits in a particular short multiplet. It has dimension 2. It transforms as a triplet of SU2R, the superprimary. So this is a superprimary. It's a scalar. It has R equals 0. I can give you a name in these classifications. So for completeness, I might write it down, but there's no added value in the name in different types of classifications. It's also sometimes called a behet 1. So it has a name, meaning that we know what shortening condition it obeys. So it obeys a condition of this type. Okay, so I think this is a good point to stop, where we finished going through a very quick summary of representation theory. And this will be essential in organizing what we mean, what is a theory. I don't want to have to rely on being able to give a Lagrangian, because many times I just cannot give a conventional Lagrangian description. So instead, I want to study operators by abstractly listing them and seeing their properties and organizing them in representations. And this is what I will start as a definition of a theory next time when constructing this map to two-dimensional vertex operator algebras that I will quickly review next time in the beginning. So I can stop here for questions.
Great. Thanks a lot, Madalena, for a very nice talk. Let's all thank her. And now we can move to the question and answer session. So maybe we can start with some of the questions that were already posted. I think you address some of them, but maybe it would be good to go over, especially for the mathematicians, some of these questions. So there was a question about how are the operators related to supercharges? So I think I'll interpret that as, what are operators, what are supercharges, and how are they related? And a closely related question was, what do you mean when you say that something is charged under U1, U1R? So I actually maybe the people can ask the questions themselves. Shrikant, would you like to go first? You can unmute yourself, and if you want, turn on your video and ask the question. Shrikant, are you there?
Yeah.
Yeah.
Okay, so I can't start the video if the host has stopped it.
Yeah, I can change the setting. And yeah, go ahead.
Hello. Yeah, so exactly. My question was what Pranav had asked. So what does it mean to say, I wanted to know what SU sub R, SU2 sub R and U1 sub R is. What does it mean to say it's charged under, I mean, how does it act on Q basically?
Very good. So, so maybe I can even answer both questions at once. So I have my superconformal algebra, and then the question, how does it act on Q? You're asking about the commutation relations of the R symmetry. So let me actually, I have an SU2R and I have a U1R, and let me absorb the U1R into like a big U2, so I add the trace bit. And now this is how it acts on a Q. So this is SU2 plus U1R generator. So if you want the tiny r would be the trace, or in my conventions -4 with the trace, and then r plus and r minus will be r. Let me not make a mistake here. R12 and R21. And the Cartan, so this makes the SU2R. And this is T1R. Would be so you see that this Q transforms as a doublet with that index of SU2R, and it has a charge, a definite charge under the U1R that can be inferred from this. So this is the action of, this is the algebra, this is generators on generators. So maybe let me ask if this answers the question.
Shrikant? Shrikant, you can unmute yourself.
Yeah, okay, now I can unmute, yeah, it does. So this capital R subscript is meant to denote the label. So is that right? So that's what it's denoted?
Sorry, which capital R?
SU2 sub R, when you write sub R,
yes, this because there will be many SU2s lying around. So
right,
the R is to remind you that this SU2 is an R symmetry. An R symmetry, as Aswin pointed out, means that it commutes with the space-time symmetry, but it acts on the supercharges, and it acts on the supercharges like this.
Right.
And U1R is to remind you there might be many U1s, but this is U1 that comes from this R symmetry.
Okay. One related question: so what is exactly a definition for multiplet?
So these are irreducible representations of the algebra. So this is the definition, which means that I start from a lowest weight state, and then the whole multiplet is, I guess, the Verma module built by this, by acting with my raising operators, which are the Qs. And I want irreducible ones. So if there's a null state, I will remove the null state and find my irreducible. And this is what I mean by superconformal multiplets. So it's a reducible representation of the algebra.
Okay, thanks.
So I think that also answered, Shoaib, did that also answer your question about?
I mean, what is the difference between the SU2 and the U1s that you are calling U1R as a, it is charge under U1? I mean, I'm not getting that.
Here, the difference between this SU2 and this U1?
Yeah, why are you saying U1? I mean, you have written the 4 charges, but why it is charge under U1R and why SU2R is a little different from that? I'm not getting from the things which you have written here.
Okay, so yeah, what I wrote here, in all fairness, I mean, to be completely, I should have called this a U2R because this is not traceless. So I have a U2R, and then I want to split off in this U2.
And U1, huh?
A U1R, and then I have an SU2R left over.
Yeah, so then why it is charged under U? Why are you saying it is charged under U1R, and what is it? How does it differ from that from SU2R?
Okay, very good. So there, it differs by the. So what I can see here is that this QK alpha, this supercharge, is a 2 of SU2R. And it has charge. If I take the trace and I only consider a trace, I believe it should have a charge. Okay, maybe -2. Because these are not the conventions I'm usually familiar with.
Yeah.
So it has a definite charge under the trace bit as well.
Okay, yeah, correct. Thanks.
And then the Q tilde, that if you remember it had the index down, it transforms as the conjugate, and it will have the opposite charge under the U1R.
Okay, thanks. Yeah, okay, thanks.
Any other questions? Let me see. Please raise your hand if you have a question.
I had put a question in the chat. Did you see that regarding projective representations?
Oh, you can ask the question now.
Okay, you see, there is a projective representation of a group where, you know, product of elements of the group go to a scalar multiple of modulus 1 times the products of the represented matrices. So that is a projective representation with certain conditions. So the square curly bracket, which is generalization of AB minus BA or AB plus BA, how do they interact? That is what I'm curious about.
Yes,
you know,
so
real representations, projective representations, they are all used, as you know.
yeah. So I think we only need
I'm sorry, I think you're muted. Hang on 1 moment.
Sorry, I'm not sure how that happened. Sorry for that.
Thank you.
Yes. So I was saying that the symmetry algebra only needs to have a projective action on the Hilbert space. Yes. So I think these are type of representations people consider. Regarding the commutators, earlier, I guess you're referring to. Sorry to scroll so much. No, that's too much. So here, I'm just, I think, specifying, maybe I'm missing something, but here I'm just specifying the the algebra, so the bilinear product on the algebra. I'm not yet making representations. I'm just saying that I have a Z2 graded algebra, so there's a bit that is even and a bit that is odd, and I have a bilinear product that is this product here that has certain properties depending on whether these guys are even or odd. So I don't think I need to talk about representations at this stage.
Thank you.
Great. Any other questions? Please raise your hand. And I had a sort of broad question about, at the beginning you stated this classification in terms of Lagrangians. Are you headed towards some classification of theories that are not necessarily Lagrangian, presented by Lagrangians?
That would be the dream. So that's like a broad and ambitious goal of many people with many different approaches, is to have a complete classification of theories that doesn't rely on Lagrangians. I think what I'll be able to show you is kind of much more modest, but it will be, so these vertex operator algebras will allow you at least to chart out a little bit the space of allowed series. So you'll see that not anything goes, and certain regions of series space are just empty.
Right.
But the classification, I think that would be the dream, and
right,
maybe there is something that can be, maybe this is a path forward, but I think we're not there yet. Yeah.
And so is this, what you're talking about, is that in the spirit of the Bootstrap program?
That's exactly in the spirit of the Bootstrap. It won't be in the numerical incarnation of the Bootstrap, but it will be exactly imposing just, associativity.
Mm-hmm.
Yeah.
Right. And one more question, maybe at the beginning you had this conformal manifold, right? So that is, if I understand right, so I'm a mathematician, by the way, so that's why I'm asking all these silly questions. But if you start with a conformal field theory and look at its marginal deformations, is that what parameterizes locally the thing you're calling the conformal manifold?
Yes, exactly. So these gauge couplings I was talking about are exactly marginal deformations. Right. So they preserve conformality. And that's exactly what parameterizes the conformal manifold. That's right.
So it's like a moduli space of conformal field theories, like a space that parameterizes all conformal field theories of given, fixing some data, background data. Is that right? Is that a sort of rough?
Yeah, exactly. So if you have a theory that happens to have exactly marginal deformation, and a Lagrangian theory with a gauge coupling is an example of that, if it's conformal, then this is a conformal direction. You can just deform your theory with this exactly marginal operator, and you keep conformality, and you just explore this manifold. I guess because of the action of dualities, maybe I should call it a manifold because there are some special places and so on. But yeah.
Thank you. Okay, I think there is a question. Someone has their hand raised. Shrikant, you have your hand raised. Would you like to?
Yeah. I had a question about. So now that the theory which you motivated is like a bunch of operators and like correlation functions defines a theory. So how does one detect whether such a theory is non-Lagrangian? Like what would be a test for non-Lagrangian? Sorry, I mean that there is no Lagrangian specifying this theory.
That's a good question. So to ask for a Lagrangian, I guess the first thing I would search for is does the theory have an exactly marginal deformation? So is there an operator that's exactly marginal? Because this would mean that even if I'm looking at a strongly coupled theory, I could try to go to a point where it becomes weakly coupled. And then I would search for, in this conformal manifold, a point where in my spectrum of operators, in my list of operators, I find free fields. So this would be some, a bit of a singular point when the coupling goes to 0, and then I just have collections of free fields. I guess this is the best I can do at trying to attempt to answer whether the theory would admit this type of conventional Lagrangian description. There has been progress in constructing different types of Lagrangians, so n equals 1 Lagrangians that flow under a full RG flow to n equals 2 series that one would have called non-Lagrangian. But remaining in the realm of just moving on a conformal manifold, I think this is how I would address it. I wouldn't know how to address the question of whether the theory has a less conventional Lagrangian, like some n equals 1 Lagrangian or something else that we just haven't cooked up yet.
So the theory, when you say theory, that means it includes all the nearby regions of the parameter variations, not like an individual, not at one point with the individual set of parameters. So because in this answer, we have to tune something and go out and see whether we can find some theory with some free fields, right? In this.
Yeah, I guess it would be a bit of semantics here. I guess I would say a theory including if there's an exactly marginal deformation and everything is a function of this parameter, and I can search this parameter space, and I would still call it, I suppose, the same theory.
Okay.
But it's, I guess, my personal semantics choice. I'm not sure if it's so standard.
Okay. Thanks.
So one more question I had about your last slide. You said, where you say what is a theory.
Yeah.
So you included the operators and how they organize into these representations. Isn't the operator product expansion going to be a part of saying what the theory is? So is that what you're going to do next time? So
yes, this is what I was going to do next time. Yeah.
Okay.
So then if you just give me a random set of operators, it won't form a consistent theory, because now I need to impose that I have a, well, not just unitarity, but I have an associative operator product algebra. So this will be exactly the next step. So in a way, maybe, yeah, let me be more clear. This is more to come.
Great. Thanks a lot. So any other questions? You can also, even if some question comes to your mind later after the talk, you can always go, ask in the Slack channel for this particular mini course. Yeah, and also during the next talk, of course. So since I don't see any hands raised, maybe we can end here for now. First, let's thank Madalena again for a wonderful talk.